So this is me. Luckily, I included a picture since you can't see me right now, and also you can't see the fact that we've been in lockdown in Canada for 14 months, so I don't have this haircut anymore. Um, but hopefully we'll be out of that soon. So I'm going to be talking about mass timber, and we've been saying for a long time the mass timber is the future of architecture, and there's a lot of good reasons for that. The biggest one is that it is really one of the only ways that we can start to meet our climate goals, not just in Canada, but you've seen in the news recently a lot of countries around the world. So we've got 88% less embodied carbon in the actual building materials itself. We're targeting 80% below ASHRAE for our energy usage, but we're also able to cut other things down. So less deliveries to site because we're delivering timber, which is relatively lightweight, and 75% less construction waste because we're making sure that we pre-plan everything and we're making good use of all of the materials. So that's kind of given this saying that less is less. Bit of a kind of joke on the less is more, but less is less for us, and that's a really good thing. Now, Gensler, we have a small office in Australia, but we're actually a huge worldwide company, and we're designing about 5 million square feet of mass timber buildings right now, a big chunk of that being for Alphabet and Sidewalk Labs. And we're also doing things like a couple of million square feet for Walmart. Their entire new office campus is going to be mass timber and net zero, and then some smaller kind of bespoke projects too. But the one we were doing for Sidewalk in Toronto is a bit of a unique opportunity. Toronto's a city right on the lake, pretty dense, pretty high rise. The new buildings going up around here average kind of 30 to 40 stories and taller. And we had this brilliant site with Sidewalk right down on the waterfront, which had its own unique challenges, but give us a pretty interesting opportunity to do something new in a big space on the water. And we actually started by digging into doing a prototype. Now, I use this image of a car prototype because when you think about it, architecture is the only design industry that doesn't build prototypes, not on any serious scale. And part of that was because it was too expensive, it was too big, we couldn't do it. But in the digital world and using all the digital tools, we actually can, and we can build them, we can test them, we can build physical smaller versions as well. And we took the approach of doing this the same way that the car industry does. They do these incredible prototype cars which test the absolute limits of what is possible. And those cars don't generally make it onto the road. They make it to motor shows, and you see them on the TV. But they're there because they're testing the boundaries, and what they learn during that gets fed back into the real projects. And that's exactly what we did with what I'm going to show you today. So as I said, this is a culmination of about 36 months worth of work, or 3 years. And we got right into the detail. And you'll see later on that we actually literally counted every single screw that was going to be in this 35-story building so that we knew how much carbon there was and where all of this stuff was being sourced from. And we started off with a pretty typical process. We had the site, obviously, we worked through the massing, the structure, and the programming. We wanted to make this as realistic as possible. So not just my team here at Gensler, but we also had structural engineers, mechanical, electrical, wind analysis. We did tunnel testing and all that kind of stuff. So we went through the full process of how this was going to work, and actually, made submissions to the city as well. Now, the first thing is you can imagine doing or designing the tallest mass timber building in the world. The tallest right now built is about 20 stories, and we're going to between 35 and 40 with this, was actually getting the structure to work. And we wanted to be, given it's a prototype, we wanted to test everything, we wanted to be total purists. So a completely mass timber structure, no concrete, no steel, trying to make it work. What could we do if we're absolutely pure in our idea? So we started testing a few things. We looked at steel braces, we looked at a concrete core, and we looked at the mass timber core. Now, for a 35-story building, and there's a lot of them in Toronto, a concrete core is the obvious approach. Now, that's fine, but if you try and build a concrete core without the floors around it, or you make the floors out of mass timber, you basically have this, 150 foot high, or 150 meter high, toothpick, which is not going to stand up. And that really didn't work. We managed to get a version using a mass timber core, which did work, but the walls for that were 5 feet thick, so about 1.5 meters thick. That's really not practical. What we actually landed on was an exoskeleton approach. Now, typically, you wouldn't do an exoskeleton in a tall building until you got much closer to 70 or 80 stories, or you're in a high seismic zone or whatever. But because the mass timber building is so light, we actually ended up having to use that approach to lateral support much earlier in the process and much earlier in the height. And here's really why. So a really lightweight building, mass timber project weighs significantly less than concrete, obviously. But down here with the blue line, you have the amount of movement that an occupant is going to be comfortable with when they're in the building. And by that, I mean, how much the building sways in the wind, basically. Now you can see the gray dot there for a concrete building, relatively low frequency movement and relatively small amount of movement. Now our mass timber project, the first time we designed it was, way out of line with what would be comfortable. And although the building didn't collapse in the wind tunnel and in the structural testing, it did move by 3 meters at the top, which is, pretty significant. You get very, very seasick if you're in that project. So we started looking at options. Okay, what if we stiffen up the frame, we improve the connections, we try and add reinforcement to it? Well, what actually happened is that basically the entire exterior of the building started to become pretty much solid. We had increased steel in the connection pieces that we wanted to keep away from. That increased the carbon in the building and it blocked a lot of the windows. So then we looked at increasing mass. Now that's a very easy way of bringing the frequency down and bringing the amount of movement down in the building. But we actually then ended up adding concrete to every single floor and concrete to the top of the building. And at that point, doing it in mass timber was basically pointless. So the third option, how do we actually make this work given the amount of movement in a pure timber structure? And that was by adding a tuned mass damper. So we added that damper to the top of the building. It needed to only weigh about 5% of the weight of the entire structure, which is surprisingly small. It's about the size of a minivan. And the damper could be made of anything. So this is the type of damper we ended up with. This is, moves in 3 directions here, and it can be tuned to the same frequency of the building. So you can install this, know roughly what the building conditions are going to be, or do within engineering limits, obviously. And then during the life of the project, you can actually tune this damper to make it more effective. The cool thing about this one as well is that those steel plates you see on top here can actually be made of anything heavy. So because we had space to do it, we looked at using low carbon materials such as recycled stone or anything like that, which could be taken out of the ground and not really processed. So our final mass damper design actually had a large amount of kind of waste aggregate material in there to provide the mass. So that was honestly nearly the first 6 months just trying to make this thing stand up. But once we'd done that, Sidewalk Labs and Alphabet challenged us to, if you're going to do this, great, but you've got to be able to build it off-site in a factory where it's safe and clean and we can drive down waste. So how do you take a 35-story building, put it on a truck, from a factory, and what kind of size and types of parts you need to do that? So prefabrication, it's great. Using my favorite prefabrication analogy, what is our Lego brick? And once we've figured out our Lego brick, we could figure out how to put the building together, and we could figure out the amount of variation we wanted. So for us, the Lego brick was one structural bay. Once we'd figured that out, we could go anywhere and we could build any shaped building using it. But that's not that simple. That one Lego brick needed to be small enough that it could be made of a single piece of mass plywood, in our case, MPP. It needed to be able to fit on a truck. And then when you assembled those bricks together, you needed to be able to create a grid that was large enough to park cars under it, had a column span that was useful for office layouts, and could be modulated to create residential suites as well. So unfortunately, none of those things line up. The material coming from the factory was, basically 12 feet by 48 feet. The maximum size that we could ship in a truck was 10 feet, so slightly smaller than could come out of the factory, which is as ridiculous as it sounds. They can create something in a factory and they can't get it to anywhere. And then none of that lined up with cars. So we actually spent a lot of time figuring out, okay, how do we combine these pieces or these Lego bricks together to make a module that's really going to work for the building? And once we'd started working through that, we realized it wasn't just, the floor and the columns that we needed, but we also needed to figure out how to prefabricate all of the structure, the columns, the girders, the floors, pieces of floor, the braced frames that we're going to deal with lateral and seismic issues, how do we prefabricate the facade panels? And then we started working with a bunch of other companies, including people like SurePods and Coney, to develop systems for prefabricated elevator cores, prefabricated washrooms, and kitchens too. So all of these pieces would come together as a kit that could build a building with almost nothing actually built on site. So here's what they look like. This is our typical one grid bay. You can see it's actually made out of 2 floor cassettes, and I'll get into that a bit more in a second. But 2 floor cassettes come together and sit on the girder, and then we leave a space above the girder for the services to run through, so that always the mass timber is the first thing you see as you walk into one of these rooms, and the services are above that. Now we're using mass plywood and LVL. LVL is essentially very similar to mass plywood. That means that you get a kind of wearing face on one side and then the edge of the plywood on the other. So just imagine these as 600 mil thick, in some cases, pieces of plywood. So plugging into that mass plywood frame or LVL frame, we then had the floor cassettes. Now we wanted to get as much of this prefabricated as possible. So we started with 1 sheet of mass plywood, 20 feet by 10 feet, which fit nicely into our grid. Underneath that, we added the ribs, which act like purlins, basically, that span in the opposite direction to the beams. And then we loaded it up with everything that you need for a building. So right into there, we're adding the acoustics above and the floor finish. Below, we're adding the fireproofing, the acoustic insulation, radiant heating and cooling, security conduit, Wi-Fi conduit, all of that kind of stuff, and a ceiling finish. And that actually forms a prefabricated piece then that we can use in multiple different ways and multiple different locations. All of that MEP and everything that goes into it, it's all pre-inspected and has one connection point, which is back at the corridor. So we can create these very clean suites very quickly. And we did the same for the facade. So again, based on a mass plywood panel, in this case, a bit taller because we had higher floor to floor height, but the same width as the structural grid. And onto that, we layered up everything that you need for a high performance facade. So the air vapor barriers or vapor control layers, tying in the windows and using passive house windows to do that. About 150 mil of insulation, and then a rain screen system. Now, the nice thing about this is, all of these pieces are laser cut in the factory or CNC'd. So we could actually take that panel, cut any size and shape window or door opening in it, create bigger or smaller windows, and then layer up our pieces on that. But the actual connection details never change. So the connection from one panel to the next, we could design and test and never change it. The connection from the window to the panel, etc. Because it was a rain screen system, you can then switch out that final decorative layer for anything you want. We tested metal cladding, fiber cement, even tested precast, which is kind of crazy to add concrete to a wood building. But all of these different systems can be integrated for a complete flexible design. Always coming back to this idea that if someone sees this building in the end and they can tell that it's prefabricated, then we've definitely screwed it up. Once we'd figured out our pieces, we then had to make sure they're safe, obviously. So we took this kind of 5-step approach, starting with stopping fires from happening and ending with getting people out, but having to deal with everything in between. Obviously, stopping fires being the main concern. How do you get them out of the building? So looking at fire data and what causes them and all these kind of different things, what we realized is actually there's 2 types of fire at this point that we have to deal with. One is electrical and the second is cooking. So both of those are very easy to get rid of. We took all of the electricity out of the building, which I will explain in a second. And we took all of the natural gas out too. So all of our cooktops and everything were run on induction, so completely cold surfaces to prevent cooktop fires. And we had no chance of electrical fires because every system in the building runs on a volt server, which is essentially a very high-tech power over Ethernet system that's running 12-volt electricity throughout the building, and it's running direct current versus instead of AC. Now that might seem like nothing would really work if you're just running essentially battery power throughout the entire building, but actually when you think about it and you look around your home, everything in your home runs on DC right now. So anything that has a motor in it, anything that has a battery in it, all of that runs on DC. And using digital electricity, we could send 12-volt packages, as we call them, of power. And if you needed more power to run something like a hairdryer or a stove, you just send more more of those packages. It's like just adding more batteries to something to get more juice into it. So that system is super effective. We've some of the offices that we've been doing with Sidewalk are now powered on this, and we have small buildings powered on Volt server as well. And you can tell how safe it is because as part of our demonstration in the demonstration lab that we had open last year, you could actually go around, pull the cables out the back of the refrigerator and stick them in your mouth, and you were fine because they're just 12-volt power. And then we got deep into the testing. So this is a good image really just to show fire testing of mass timber. And you can see that it looks seriously charred on the outside, but actually the timber on the inside remains relatively untouched. And there's been a lot of testing around the world on this now, but we did our own stuff just to double check it and using different products. And essentially you can get an hour's fire rating on a piece of timber by adding 25 mil of what we call sacrificial timber to the outside. So that burns away, forming an insulating layer that protects the timber. So as long as you oversize your structural elements suitably, you can very quickly and very reliably get 1 hour, 2 hour, 3 hour protection on your beams and columns and floors. And of course, we also tested our assemblies. So in the image here, you're seeing on the left is one of our floor cassettes being tested. And this is after a 2-hour burn, so you can see it stayed in place. On the right is actually a compliant 2-hour drywall sealing. It wasn't until we started doing these testing that I realized that drywall is actually flammable. So after 2 hours, you can see the drywall here on the edge is actually on fire. But that compliant sealing, even though it collapsed after 2 hours, is still compliant because it stopped the flames going through. Obviously, our system, with a lot of R&D and effort put into it and using some different spray applied plaster systems, is not just 2-hour compliant, it's also firefighter safe because it's not going to fall on them as they come into the building. And on top of that, we added the best in class life safety systems that we could find, and that included mist sprinklers. So very similar to a normal sprinkler, we have a pressurized water line, but instead of using kind of typical faucet or tap pressure, we're actually using a really high pressure through a 12.5 mil stainless steel conduit. What that does is spray a high mist fog out, and that puts out fires very quickly. It also has the advantage that it can, it's in the air, it gets under tables, it gets into cupboards, and it will actually put fire out in places where it can't physically see the fire. Now, this system is very effective, but it also has the advantage that it uses about 10% of the water that a typical sprinkler system uses. So, this isn't actually about water conservation. This is about not flooding a wood building with hundreds and hundreds of liters of water and making all of the wood warp and swell and that kind of thing. So 10% of the water was a lot safer for us to put into a wood building without really damaging the building itself. So that's all the technical side. Then we had to really get into, how do we design this? So as the building kind of stacked up and we figured out the pieces, we realized we could do a very simple tower like this. And we costed this one out. We had 2 contractors look at it. And this was right on budget for a tower in Toronto. So equivalent to a concrete tower. And then we did some kind of fun versions as well, playing up the cross bracing, using different prefabricated facade elements to just see what we could actually do and see if we could make it more interesting. And the same on the inside. So this is actually the ground floor of the 35-story building. This is using the fully engineered model. So you can see the connections there. You can see the cross bracing that exists. But these columns that everyone expected to be really huge actually aren't too bad in the space, and the column spacing itself is quite nice. And that worked out well for the unit plans as well. So in a typical residential unit, you can't expose the timber ceiling because we need that buildup that I showed you for the acoustics from floor to floor and for fire protection. But you will be able to see the typical beams and columns and the ribs and purlins. So you get this really kind of nice natural Scandinavian type feel to it. So sustainability, this was really the last thing we tackled, knowing that we'd all the way through designed to passive house standards. We'd used low temperature radiant to heat and cool the building, which is very energy efficient. And we wanted to see how well we'd done before refining that down. So we started measuring 2 things. As people will know, 11% of all of the carbon emissions in the world come from construction. It's about 4 or 5 times more than comes from the entire airline industry. But somehow we kind of dodged the bullet on that. And the airline industry gets in trouble. But of that 11%, half of it comes from building the buildings and the other half comes from operating. So that means when you build the building, you're burning 50% of all of your carbon in that 1 year or 2 years of construction. The actual energy use to operate a building is very, very small in comparison. It's about 1% per year for the 50-year life cycle of the building. So we tackled embodied carbon first. Now, there's kind of controversy over where embodied carbon sits in mass timber projects, but just as a baseline, if you delete the concrete frame above grade and switch it out for mass timber, you're going to make about a 40% saving in embodied carbon. And that's just really on the energy used to create and process the materials. If you take into account sequestration, which is this idea that a tree grows and when it reaches its maximum height, it's absorbed all the carbon it's really going to absorb in its life. You cut that down and replace it with a new one, and you put that tree to good use. Then you can actually get down to about 8% of the carbon in a concrete building. Now that's really important that we're showing both numbers here because there's still some controversy around whether sequestration counts and how much of it you should count. So we're using both numbers just to be totally transparent. And when we got into energy usage, as I said, we were passive house quality on the facade. We're using low temperature systems inside. But what you can really see very quickly is that the biggest saver, the window to wall ratio is great. We're about 40%, but it was air leakage was the big first saver. So if we could get that air leakage down, create a really tight facade, we could instantly save about 21% of the energy of the building. Now, if we didn't do that, then nothing else that we do for the rest of the project would even help. So it's like the boat analogy. You can have a really great boat. If there's a hole in it, it's not a boat anymore. And that's the same applies to the buildings. So don't put any holes in them, and then we'll go from there. So improve the glazing, got another decent saving. So we're down 35%. And then everything else relies on the MEP systems. Now, the facade and glazing performance is super important because if you don't get that first 35% of savings, you can't switch from a hot air system or a chilled air system to a radiant system, and therefore you just won't see the rest of the savings. So with all that in mind, we're about 70% less than the code requirements or less than the ASHRAE requirements in terms of our energy use. And that's with actually allowing any tenant in the building to do whatever they want. So the rest of that 34% of energy, basically all of that is an assumption that a tenant could come in and put some kind of crazy 100-watt bulbs in their unit. And the very cool thing about this, we actually added this slide when there was the big storms in Texas a few months ago, that our buildings in a severe weather event, if it goes below 0, and I apologize, these temperatures are in Fahrenheit, which I don't understand. I'm pretty sure you guys won't understand it in Australia either, but 40 is 0 for no reason. So if the outside temperature goes below 0, our building will actually last several weeks before the internal temperature drops down. And that's really just because of the air tightness in the insulation. And what you won't see is the problems they had in Texas, which was the building and the building occupants freezing within the first 6 hours of the severe temperature drop.